Okay, so then let's get started. So yeah, in this course, we are discussing lots of some kind of the representations for this 3D data. And until now, we discussed like a bunch of some kind of the representations and some kind of the ideas in terms of how we can encode and decode those kind of things. And recently, we are discussing the basically some ideas about the neural rendering with some kind of the two different kind of representations. The first one was basically the NERF, which is the most representative, the idea for the neural rendering, which is purely implicit the representation, basically implicitly like representing the 3D scene with the radiance and the opacity in terms of that we are using the volume rendering the equation to render these things into the images from each of the view. And some other kind of the more sort of the more explicit representation was the Gaussian splitting, which is basically fitting some kind of the 3D ellipsoid in the scene while we are still using the same the volume rendering the equation for the rendering. So these are some kind of the ideas in terms like leveraging the volume rendering equation while reconstructing the 3D from the multi-viewed images, right? But not only this kind of thing, actually also for the 3D Gaussian splitting, so we are also seeing lots of the interesting the applications in our the gas vectors, right? So how we can also do this kind of reconstruction for the very large scale the scenes, and also for some kind of the dynamic scenes as well, and how we can also use the bitboard, the networks for those kind of reconstruction. Those are some kind of the ideas which also has been introduced very recently in some kind of research papers. And these are kind of interesting topics that we could see in the 2D data structures. But not only this kind of thing, actually in this course, we are discussing a bunch of the other representations as well, like the voxels and the multi-view images, point cloud and mesh. And those kind of the representations basically have some kind of the pros and the cons. For some of the applications, it might be better to use the point cloud. For the other applications, it might be used the mesh, and depending on the kind of the applications, right? So one quick question might be is that how we can do also some kind of the conversion from the NERF for the Gaussian splitting the representation into the other representations. So I guess you might already have some kind of the ideas for this, but basically there are some kind of some sort of some ad hoc the kind of the approaches in terms of like how we can also get some kind of the depth information from the NERF. So if we basically revisit the volume rendering the equation, basically what we can see is that basically this term, the multiplication of the transparency and the opacity here was basically some kind of the weight for each of the point, right? Representing how likely the ray will stop for each of the point. So based on this kind of the probability in terms of like measuring the likelihood of the determination of the ray at the point, if we basically find the point which is giving some kind of the highest probability of determination, that we can basically choose that point as kind of some kind of the depth from that point, right? So that can be kind of some kind of the simplest way in terms of that we can convert the NERF representation into the depths. And this information can also be used for some kind of some implicit representations for these reasons. While obviously the quality may not be very good because the NERF was basically trained not to obtain the geometry, but also just for some kind of the rendering, right? So actually, we are not gonna get into any details for those kind of things, but there are actually very lots of some kind of the recent research which is about focusing on like doing something like the neural rendering, but not to basically get some kind of the clean images from the multiple views, but more focusing on basically getting some kind of a signed distance function, still using some kind of the same the scheme in terms of using the volume rendering the equation and doing some kind of the multi-view based 3D construction. So if you are interested in these kind of things, I also recommend you to check out those kind of these papers in terms of how we can also obtain the precise sign distance function from the multi-view images. And also speaking to the 3D, the Gaussian split, also for the Gaussian splitting, we can do the same thing in terms of like calculating the transparency and also the opacity. We can also try to estimate predict the depths from the given the reconstruction. But there are also some kind of a very recent work in terms of like how we can fit not the 3D ellipsoid, but actually the 2D ellipses. So basically, we are switching from the 3D Gaussian splitting to the 2D Gaussian splitting, not using the ellipsoid, but the ellipse. In terms of that, we see more precise alignment of the ellipse 3D surface in a way that we can also get some kind of the precise the depth information from the Gaussian splitting. So these are some kind of the basic ideas in terms of the how we can also convert some kind of the neural rendering the outputs, the nerf and the Gaussian splits into some kind of the implicit function like the depths in a way that we can do some kind of the conversion into the other representations. So actually, in the beginning of like this course, like we are discussing about some kind of bunch of the representations and how we can do some kind of the conversion across those kind of representations. And if we see these kind of the representations, but we can basically see that the conversion from the implicit function into the voxels is very straightforward. We just need to evaluate the function for each of the voxel, right? So this is the simply the case. And also the conversion from the mesh to the point cloud and mesh to the multi-view images is also quite straightforward in terms of that we can just like sample the points over the surface and just render the mesh into the multi-view images. But the thing is that the missing kind of the bridges across those kind of representation is that how we can do some kind of conversion from the point cloud into the basically the voxels into the mesh. Then we can do the all this like way of the conversion all the way from the implicit function into the point cloud. And if we want to make a loop from the point cloud into the implicit function, then we need to have another kind of the way to convert from the point cloud into the implicit function. So for this week and the next week, we are going to see basically how we can, fill in this kind of the bridges across all the representations in terms of that we can basically change the representation like from one to the other. So that's the basic idea. Question here is that for the 2D Gaussian alignment, is it necessary to have the surface normal supervision, or is that also input from the RGB loss? So the typical the recent work is also estimating the normal as well. So that's really good question. So even without like having any kind of the given the normal information, the recent work is basically introducing some kind of the ideas in terms of how we can fit the basically the 2D ellipse over the surface. So that is actually giving some kind of the surface information. Yeah. So, but obviously, since we are not really having some kind of any geometry information, but just using having the color images, actually the ellipse, the normal information given from the ellipse may not be that precise. So there is no guarantee that basically the ellipse will be precise or aligned over the surface. But the interesting is that empirically, typically when if you use the 2D Gaussian splitting, then you can see that the ellipse is, in most of the cases, is like precisely aligned over the surface. Yeah, that's a good question. So yeah, basically we are seeing some kind of all the ways, like we are doing some kind of conversion from the some Gaussian splitting into the implicit function, and also the implicit function into the voxels and the mesh and the point cloud. And here basically the two missing thing is that how we gonna do some kind of conversion from the point cloud into the implicit function, and also basically the voxels into the mesh. So we are going to discuss those kind of the two ideas for in the couple of weeks. Okay, so if we just like recap, the roadmap that we are seeing in this course, basically now we are going into the kind of the here, basically we know how we're gonna do some kind of conversion from the like one representation to the other. Okay, so so basically let's see basically how we can do some kind of the conversion from the point cloud, the implicit function, and the voxels into the mesh. So the first thing is that how we gonna basically get some kind of signed distance function from the point cloud. So here the basic idea is that let's say we have some kind of the n number of the points which is sampled over the surface, and based on that we are going to get some kind of the signed distance function which is zero level set is basically approximating the surface, which means that if we basically find some kind of the points which the function, the value gives some kind of the zero value, that becomes the points over the surface, right? And we know that the given the points in the point cloud is basically the points over the surface, which means that if we evaluate the output function f for all the points that we have, the evaluation of the function should be zero for those kind of the points, right? Then if we find such kind of the function f here, what will be kind of the trivial the solution for the f? So we are basically having some the condition for the function that we are going to find here, right? So we are basically finding a signed distance function f which should satisfy this condition. For all the points, the output of the function should be 0, right? And then if we only have this condition, the problem is that the trivial solution becomes a function which outputs 0 for every error, everywhere in the space, right? That will be basically the trivial solution. And obviously, we want to basically avoid such kind of the trivial solution, right? Which means that we need to have some kind of the constraints or some kind of the assumption. So we are going to see some kind of the ideas, basically how we are going to into some kind of some more the conditions or some kind of the assumption. So here basically one thing is that one simple the idea is that we are going to assume that the function f is kind of the polynomial the function like this. Which is basically we are assuming that the surface is locally represented as some kind of polynomial the function. So here basically what we can see is that we are now approximating the function into this form as some kind of order of the polynomial functions. And now we are also going to basically rewrite this function into this way. So you can now see that the vector A is representing the coefficients for each of the terms here. And B is basically the function which basically the outputs the polynomial the terms in the function. So if you have basically the point with the x, y, z coordinates, that B is basically returning basically the vector with some kind of all the polynomial the terms here. And then we are basically having the A here, which is the coefficients here. So here the goal is that we are going to find a polynomial the function here, which the coefficients becomes not 0. So if we find like all the function which all the coefficients are basically the 0, that becomes the trivial solution. And we are going to find a function which the coefficients and like none of any of there are some kind of the non-zero the coefficients in the given the function. So how we can find such kind of some non-zero parameter is kind of the problem that we have, right? So basically, here the question is that how to find some kind of the non-zero the parameters A, the vector here. So for that, what we can do is that we could basically simply use the least square approximation. So basically, what we know is that the function, the value for each of the points that we have should be 0, right? So we are basically minimizing the square of this kind of the function, the outputs for all the points, while finding some kind of the non-zero the parameters A here. So that's basically that what we are going to do. Very straightforward, right? The thing is that obviously the function that we are, the surface that we are going to reconstruct would not be, for most of the cases, it will not be basically represented as a like single the polynomial the function. The surface that we are going to reconstruct might be basically more the complex the shape, right? So here the idea is that we are not basically fitting the polynomial the function over the entire surface, but we are going to do this kind of fitting only for the local region. So let's say like we have some kind of the n number of the points, and then given any kind of the query point that we are picking in the 3D space, the simple idea for this is that we are basically simply taking some kind of some local neighbors for the given the query point. And we are only using this kind of the local neighbor points to fit some this kind of polynomial function, while basically assuming that the local the neighbors can be approximated as kind of some polynomial function. So that's the basic idea. So that's the basic idea for the moving least squares. But typically what we do for the moving the least squares is that in terms of like the fitting the polynomial function in the local region, instead of like taking some kind of the local neighbors, actually we are going to define some kind of the weight function. The weight function in terms of that as the point is close to the query point, the weight becomes the higher. And as the point becomes like the farther from the query point, the weight becomes the lower. So it's not basically explicitly basically taking some kind of the local neighbors, but define some kind of the weight function based on the distance from the query point to all the points that we have. So that's the kind of the basic idea. So this is the same form of the least squares. The only thing is that now we are basically introducing the weight function like this. And you can see that now the weight function is defined based on the distance. So I'm basically introducing basically this notation. So this is basically a function which is taking the distance as the input here. This kind of the function is basically called the radial the function, the radial the kernel, right? And then we are basically rewriting basically this term by basically having this. So instead of like having the pi here, we are basically using this notation. And this is the weight function. Not to explicitly define they take the locally neighbors, but basically say basically which points should be giving some kind of the more impact in terms of the fitting some kind of the polynomial function. So that's the basic kind of the idea. And obviously for the weight function, we can use any kind of the function that we want. So there are also kind of a bunch of the options for this. We can whether use some kind of the Gaussian might be some kind of the most the common choice for the weight function. But instead of that, we can consider using some kind of the other types of the function. Also, this kind of the inverse the quadratic and the inverse the multi-quadratic, those are also the widely used as kind of the weight function for the least squares. So let's say we are basically defining this kind of the weight function. And then here the question is that, so we are basically solving this kind of the optimization the problem, right? So for each of so we are basically having any kind of query point x here. For all the points, the pi that we have, given the weight function, now we can compute the weight here, right? And also this like b term, this is basically the vector of the polynomial terms, which can be also computed based on the XYZ coordinates for the pi here, for all the points that we have. So given this kind of the information for the weights here and the polynomial terms here, here the question is that how we can find the best parameter A, which is the coefficients defining the polynomial function while basically minimizing basically these weighted least squares. So that's basically the basic idea, right? So now we can see that the weights are basically determined based on the query point and all the points that we have. And for each of the point, the input point, now we can obviously calculate the polynomial terms here. And here the question is that we are finding the best the parameters for the coefficients for the polynomial function in terms of minimizing this kind of term, the weighted the least squares. So this is basically the problem that we are going to solve, right? So how we can find this kind of the best the parameters A here? So we are basically going to define this kind of the two matrices and the B and the W here. It's basically nothing but basically we are basically stacking this kind of the polynomial the terms here, the B vectors here, and making a diagonal the matrix with the weight that we have. For the given the query point, we are calculating the weight with respect to the for each of the point and making a diagonal the matrix like this. And based on these, the definition of like these two matrices, the weighted the least square the function is now can be rewritten into this way into the matrix form. So you can see that now the square term here can be with the weights here can be rewritten into the matrix form like this, and then this can be rewritten like in this way. So like all these are like the weighted least squares now it can be written as some kind of simple the matrix form like this. And here the question is that actually we wanted to basically find some kind of the parameters, some non-zero parameters here. Otherwise, we are basically having some kind of the trivial solution, right? So now the optimization the problem becomes that we are actually minimizing this function with our the definition of the m here, while basically having some kind of the constraint, the non-zero constraint for the a here. So as the non-zero constraint, actually we are going to assume that the norm of the a should be 1. So this kind of the optimization actually turns out that actually we are solving this problem. And actually this problem can be basically solved as kind of the eigenvector problem. Can you see why? Like actually why this optimization becomes a eigenvector problem? Any thoughts on this? If you took any kind of the optimization the course, then you would be able to quickly say that actually this can be seen as kind of some eigenvector problem. Uh, Otherwise, I'm still, if you do not have any kind of knowledge about the linear algebra or some, optimization, actually, if you see the same problem for the other applications as well, then you'll be able to basically utilize the fact that actually this can be basically solved as kind of the eigenvector problem. Yeah. So this is kind of like very typical kind of form that we can see in many applications. We are basically minimizing this kind of quadratic terms, which is basically convex problem with some kind of the the constraint for the vector that we have, right? So in this kind of the case, actually, we are not getting into any details about this kind of the optimization kind of literature. But what we can see, if you took the optimization the course before, is that actually this kind of the convex problem with some kind of the constraint can be solved by this kind of the Lagrangian like this. So the basic idea is that now we are basically solving another kind of the optimization the problem by just taking these two as some kind of linear combination. So this is kind of the original the forming the optimization. And we are basically introducing some kind of some weight, which is called the Lagrangian the multiplier for the condition that we have. So the basic idea is that we first solve this problem, basically minimizing this Lagrangian over the original the variable a here. So taking the gradient of the Lagrangian here in terms of like basically seeing like what should be basically the multiplier of the lambda here. So by basically solving the minimization over the Lagrangian with the variable a here, what we can see is that the lambda basically should be this is basically new the variable which is the Lagrangian the multiplier, and this multiplier basically should satisfy this kind of condition. The ma should equal to the lambda a, and we can say that this is exactly the eigenvalue and the eigenvector form, right? So from this, what we can see is that this A and the lambda basically should be the eigenvector and the eigenvalue of the matrix M. And here the question is that what's the basically one of the the value which is basically minimizing this term, right? So if we go back to the original optimization, this term here, then now we can rewrite this by replacing this MA here into the lambda A here because that's the condition that we have seen. Then we can see that actually the original this problem becomes like minimizing the lambda here. And we have seen that the lambda should be one of the eigenvalue. So which means that this original the optimization becomes so this term is basically minimized when you choose the smallest eigenvalue the lambda here. So when you choose the smallest the eigenvalue for the lambda here, actually we can see that the A also should be the corresponding the eigenvector. So basically, while the optimization basically looks kind of complicated, what we can say is that once we basically compute this like the M matrix, this basically A the vector, which is minimizing this, can be basically computed by finding the eigenvector of the M, which is corresponding to the smallest the eigenvalue. So this is actually very simple kind of problem in terms of we can easily find the coefficients of the polynomial the function based on by solving the eigenvector the problem. Clear? Any questions on this? The only thing is that actually depending on like how we choose the weight function, we're gonna get some kind of the different results. Even when you choose the Gaussian kernel as kind of the weighting function, depending on some parameters that we are choosing here, for example, like what sort of the h that we choose here, we're gonna get some kind of different results. So based on some kind of the density of the points and many other kind of like noise, like many other things, based on that, we can carefully choose some kind of the weighting function in terms of that we are getting some kind of the better the outputs of the final the shape given the point cloud. Here the question is that if when you see this kind of the two outputs, which one would be the kind of the results with the smaller the h? Do you have any sense of this? Yeah, so as many of you say, like the answer is the left, right? So if we see the meaning of like this weight function, as we basically have the smaller the h, the kernel function will be basically the pickier the function, right? Which means that we consider like more some kind of a smaller kind of range of the points near the query points, right? As we increase the h here, which will become basically the wider the corner function, which means that we consider like the more like wider range, the points in the wider range, right? Which will basically result in basically making the smoother the output function like this. But while we increase the function, the value h here, we're gonna basically make some kind of more like uh, some kind of the rough shapes in terms of that we only consider some kind of the very local the points in terms of like choosing, determining this kind of the sign distance value. So depending on like how we choose the corner function, the weighting function here, we're gonna get some kind of slightly the different outputs. Clear? Any questions on this? So this is kind of the basic idea in terms of like how we're gonna basically get some kind of some approximation of the sign distance function from the given the point cloud. And also here, the thing is that if we only consider any kind of the high order kind of things, but if we only consider like some kind of the first order the approximation, basically making the function to be like function like this, like linear function, what we can see is that actually this becomes like doing some kind of the plane fitting for each of the query point, right? Especially the query point is a point over the surface. Then we can see that this kind of fitting becomes like fitting a plane over the surface. And actually, if we could basically do some kind of the fitting of the plane over the surface, that is basically giving some kind of some important, some geometric information, which is the surface normal, the information. So basically, the surface normal is defined as kind of the vector, which is the perpendicular to the tangent plane, which is basically the best approximating the local region over the surface. And actually, you can see that this surface normal information is actually used in the wide range of the applications. Actually, what we also have seen in the discussion of the Gaussian splitting is that we discussed the subfields. I don't know whether you remember like that, we discussed the subfield. So the idea of the subfield is that now we are treating each of the point as kind of the disk to render the point cloud into the images. For those kind of the cases that we use, we render the points into the images by seeing each of the point as kind of the disk. We obviously need some kind of the surface, the normal information. So the surface normal is also used in the point cloud rendering, and also like when you encode the point cloud into the something like the point network, some kind of the other the architecture, we can consider not only feeding the x, y, z coordinates, but also the normal information as well. So the surface normal also can be used as some kind of the additional the geometric information when you encode this kind of some 3D the data. And we're going to also see that actually the surface normal also can be used to improve the 3D reconstruction as well. When you do some kind of conversion from the point cloud into some implicit function, actually the surface, if we have the surface normal information, that can be actually quite useful in terms of like improving the reconstruction quality. So the surface normal is actually widely used in the many applications. And actually, what you can say is that if we do this kind of the least scarce sense of kind of fitting, in terms of fitting the plane over the surface, that is giving us some kind of the surface, the normal information. So basically, what we can say is that actually what we have seen in the previous slide was that basically we are doing some kind of the fitting for any arbitrary query point. But now we want to do this kind of fitting for the point sampled over the surface. So let's say like the x point here is the one of the point over the surface, and we want to estimate the surface normal at this point x here, by fitting the tangent plane at the specific point. And based on that, basically what we can do is that, so let's do the same thing, doing some kind of the least square fitting. In terms of that, now let's say the PI is basically having some kind of the D3 coordinates, xi, y, and xi and yi and zi. Then what you can see is that the least square fitting the problem becomes like, can be rewritten in this way. nothing but just like rewriting this like the first order the equation here. And then what we can easily do is that we can simply like reparameterize the A vector here. So we are basically having the coefficients in this kind of the linear function here. And now we would like to basically reparameterize this basically A vector in terms of that these three A1, A1, A2, A3, these three values should be basically representing the normal vectors. And then rewriting the A0 as basically minus X transpose N. Then we can say that this becomes the typical, basically the plane equation. So this is nothing but like we are rewriting this kind of the linear function here in terms of not using these kind of for the parameters for the plane equation, but just using the plane normal the parameters here in terms of using the plane equation like this. So this is the same basically the least square defeating the problem with the weights here. But rewriting this equation in a way that now we are not finding the best parameters n here, but finding the surface, the normal, the parameters n here. We some slightly change the equation. Does it make sense? Then now we know how we can basically find the best n here, right? So here also the same the n can be basically the best n, like minimizing this also can be found by solving the eigenvector the problem, right? So can you basically see like, given this kind of the least square defeating the problem, how we're gonna basically define the matrix M and also solve this kind of the problem by just taking the eigenvector of these kind of the matrix M. How should we define the matrix M in this case? So if we basically recall what we have seen in the previous slide, the matrix M was defined with the B matrix and the weight matrix, right? So you can see that it's just the matter of like how we define the B matrix, right? So this is like almost the same form with the optimization that we have seen in the previous slide. So what we just need to do is that now we just need to define the B matrix like this way. With this kind of the vector connecting like these two. And if we use the same the weight the matrix here, based on that, now we can calculate this M matrix. And then we can, if we take the eigenvector corresponding to the smallest the eigenvalue, that becomes the surface normal the N here. So that also becomes some kind of the simplest way, and also kind of like that's the common way that we can basically estimate the surface normal from the given the point cloud. So it's also the matter of like how we define basically the weight function, the theta here, right? But you can say that the same idea also basically can be used to basically estimate the surface normal. And you can also see that actually the basic idea is also the same, exactly the same with the principle, the component analysis. If you took any of the some machine learning or the AI the course, then you would know the basic idea of the PCA, right? So the only different thing is that we are the center of the point cloud, instead of like taking the center of the point cloud, now we are doing the same thing for the given the query point X here, right? So basically, when you take the X as kind of the center of the point cloud, if we compute this thing, this becomes like actually computing some principal direction, given some kind of the points with some kind of the weight that we have. And if we choose the direction with the smallest the eigenvalue, that becomes some kind of we are treating this as kind of the surface, the normal, the direction. Makes sense? So this is the very simple and also basically the common the idea in terms of like how we can also estimate the surface normal from the given the point cloud. But what will be kind of the issue, like when you estimate the surface normal in this way? What will be kind of some kind of the missing the piece in terms like estimating the real the surface normal for many kind of the applications. Can you see like what we kind of be some more like some sort of the some missing kind of component in terms like estimating the surface normal in this way? Yeah. So I mean, obviously there might be some kind of issues in terms of like noise sensitivity. So like how are we going to handle some kind of noise in the point cloud is kind of like another kind of issue. But one thing that I wanted to bring up was that actually typically the surface normal is basically defined in a way to basically define the inside and the outside of the surface as well. So either the surface normal should be basically heading to some kind of the outgoing direction from the surface, or like inside the direction for all the points. But if we estimate the surface normal in this way, then it's basically hard to still like define some kind of like whether which one is basically the outgoing direction and also the incoming direction. So there can be some kind of cases that the normal is basically the flipped for some of the kind of the points, which means that we need to somehow also like further optimize the kind of the sign or the flipping of the normal direction in terms like having the consistency of the orientation for all the normal directions across all the points. So we needed this kind of some additional kind of the optimization the step in terms of making the orientation of the surface normal to be consistent across all the points. So that's kind of some additional thing in terms of that we need to do in terms of like estimating the surface normal. So we are not going to get into some details for this, but this is kind of the basic idea in terms of how we're going to basically estimate the surface normal. So for the given the point cloud, actually there are some kind of cases that the surface normal is also coming from the some scanning kind of devices as well. Or if the surface normal is not given, that we can consider estimating them using this kind of the idea. Then here also the question is that if we have this kind of some additional the surface normal information, or either we are estimating that or we are assuming that the surface normal is basically given, then would there be some kind of the other way around in terms of like basically computing the signed distance function from the point cloud, but without explicitly fitting some kind of the polynomial the function for each of the query point? Without basically having any kind of explicit like fitting of any kind of some explicit function, is there a kind of like any way that we can optimize some kind of implicit function globally for all the points, given the point information and also this kind of given the surface normal information? So that's another idea in terms of like, on how we can still do some kind of conversion with from the point cloud into the implicit function, but using some kind of the additional the surface the normal information. So typically what we can do is that the moving least square, the idea can be good in terms of estimating the normal, but still it's basically doing some kind of the local fitting. So it may not be basically giving us some kind of the consistent the information for the fitting across all the points. So what we can do is that we are using the moving least squares only for estimating the surface normal for each of the point, and we can consider using that the normal the information to some kind of the global the optimization of the implicit function over the entire the space. So that's one of the idea for that is basically the radial the basis function. So here the basic idea is that now we'd like to basically represent the implicit function as kind of some weighted sum of the radial the basis function. So now we see that the output function, the implicit function that we want to get, the sign distance function is representing in this way. Basically having some kind of the radial the basis function here and having the weights here. So this is also kind of given the corner function that here. And here the question is that what sort of the weights that we are going to use here. So here, like one small difference is that now this radial basis function is not some kind of the weighting function. So it doesn't need to be high when basically some kind of the other point is close to the quarry point. We can consider using any kind of the radial the corners. So there are actually the more options if we consider the other kind of the radial corners. And these are also some kind of the typical, some kind of corners that we are using for this kind of the radial the basis function, the approximation. And also, actually, many people are using this triharmonic function, which is nothing but just like having the cubic of the distance. So we can consider using any kind of the radial corners for this kind of the fitting of the process. And actually, this is kind of some approximation that we have seen in our previous lecture. Do you remember when we have seen this kind of some radial basis the approximation in our previous lecture? Anyone who remembers like when we discussed this approximation using the radial basis function? Actually, if we recall like what we have discussed in the feature networks, when we discuss some kind of the theoretic kind of aspects of like how we can guarantee like this kind of the impact of like the parameters in the Fourier the feature networks. Actually, we have seen this kind of the idea of the kernel regression. So here the basic idea is that given any kind of some data set, which is having some kind of the input the point and the output the value, we are basically finding a function approximating like all this kind of the training the data with this kind of some kernel regression the form. In terms of that, we are having some kind of the predefined kernel function here. And the thing is that for each of the data point that we have in our training the data set, we are basically having some kind of the parameter that we want to optimize, some variable, right? So this was the basic idea for the kernel regression that we have seen in the discussion in the Fourier feature networks. And we also have seen that training the neural net was basically doing something similar with this kind of the kernel regression. We have seen some kind of some connection between the deep learning, the training, the neural network training with the kernel regression, right? And you can see that actually what we are doing is exactly the same thing, right? So given the query point, not the query point, given all the points that we have in our point cloud, we know the output value, right? What should be the output value? We want to approximate the surface as the zero level set of the function, right? Which means that given all the points that we have in the input, the point cloud, we know that the output value should be zero, right? And we want to basically approximate this kind of given the training data, given the set of the points, with some kind of some function, which is basically having some kind of weighted the sum of the kernel function like this. And we are basically optimizing these weights in the least security sense like this. So basically what we are going to do here is that basically the same thing. The only thing is that here the xi becomes of the pi, basically the point in the point cloud. We know that the yi should be 0. And we are choosing any kind of the kernel function here, in terms of that we want to basically find some kind of the optimal weight here. Make sense? But then what would be the problem? Actually, we are seeing some kind of same problem here, right? So the only condition that we have is that for all the points, we know that the output value should be 0, right? And we want to find a function here, which is approximating the surface, while we find some kind of optimal weight here, right? What's the trivial solution again? Yeah, the trivial solution is basically making all the weights for all the points to be 0, right? Then there is nothing we can do. So this means that in this setup, we still also need to have some kind of the more condition or more constraints. And to give some kind of the more condition or the more constraints, actually there are a bunch of the ways, but the simplest idea in terms of avoiding the trivial solution is to use the numerical information. In terms of that, what we're going to see is that we are going to take some kind of the off-surface points based on the surface number. So what we do is that given that we are having some kind of the n number of the points, since like all the points should have the output of the function value, the function should be the zero, right? We are taking some kind of the off-surface the points along the normal direction. So let's say that we are having the consistent number, the information, the surface number information for all the points. Then we are taking like one the point outside of the shape and also the other point inside of shape. Just like taking the offset of the points along the normal direction. And then we are just assuming that the signed distance value at this kind of the surface point should be basically the distance from the point that we are taking over the surface. So let's say we take this point, and this is these two are the off surface points, right? So let's say this is the one which is the outside of the surface, and this is one in the inside of the surface. It also depends on how we define the sign distance function. But if we want to make the positive distance to the outside, then we can set that this offset, the distance here, becomes the sign distance, the value at this point. And we are also taking the minus of the distance as the sign distance value at this point, right? So given the n number of the points, we are just basically adding the 2n number of the more points with some kind of non-zero value for those points, in a way that we can basically avoid some kind of a trivial solution. Make sense? So this is like very simple the idea in terms of that given the n number of points, we're basically just like adding the two n equations with some kind of the non-zero values here. And based on that, we are just finding some kind of the best weights, which is exactly the same idea with the kernel regression. Make sense? So how can you find the best weights? Well, I mean, this is nothing but just like solving some kind of linear system. So like one row here becomes like one equation. For basically, we are also going to define the weights for all the 3n number of the points because we are now having the off-surface points as well, right? And then we are having the 3n number of the equation, making each of the row to be one of the equation. And stacking all the 3n equation, then we're gonna have this kind of linear system. And then it's just a matter of like solving the very big linear system with the 3n by 3n, the size of the matrix here, right? So this is also kind of another idea in terms of that we can now not just like doing some kind of local fitting, but doing some kind of the global optimization in terms of getting some implicit function over the entire space. Make sense? Any questions on this? So these are some kind of the outputs that we are getting the signed distance function from the point cloud. So actually now we are seeing a mesh here, right? So which means that we are doing the conversion from the point cloud into the implicit function and then evaluating those functions into the voxels and then converting the voxels into the mesh. So we also get into like how we're going to convert the voxels into the mesh, right? And this is the final output of like converting from all the way from the point cloud into the mesh like this. And you can see that we are getting some kind of quite precise outputs with all the details here. So we can get this kind of the good output image when you have some very dense and noise-free kind of the point cloud like that as the input like this. Make sense? Yeah. And also, it is also very important to choose the offset distance. If the offset distance is like too small or too big, we're gonna get some kind of some bad outputs like this. So this is kind of like some kind of downside of this kind of idea in terms of like, still we are having some kind of the parameters to get some kind of the best output in the final reconstruction. Okay. So if we compare the moving least squares and also the radial basis function, so these are some kind of the two ideas in terms of like reconstructing the final outputs. The pros and the cons of like each of the idea is that the moving least square is basically may not be the optimal the idea in terms of that we are still doing some kind of the fitting in the local region. So we are not basically seeing some kind of the global shape. So there might be some kind of some slight the inconsistency for the fitting across all the points. while the radial basis function is the case that we are doing some kind of the global optimization in terms of that we can get some kind of the complete and also the smooth the implicit function over the entire the space. But the good thing of the MLS is the moving least squares is that it does not require the surface number, but actually this idea is being used to estimate the surface number in many applications. But for the radial basis function, we first need to estimate or we need to assume that the surface number is basically given. So that's kind of the pros and the cons. And obviously, the radial basis function will be much slower because we need to solve the giant the least square problem. While the solving the eigen the vector the problem for the moving least squares would be basically solving the problem for the much smaller the matrix. So it will be much faster. And also typically the radial basis function is like more sensitive to the noise because we are basically solving some kind of the global optimization. So which means that any some kind of small noise in the points can affect not only the local region, but also for the other regions as well. But typically for for in terms of like the capturing some kind of the details, like solving this kind of the global optimization can be better in terms of getting some kind of the high quality the outputs. So there are basically some kind of the pros and the cons. If we want to basically spend more time to get some kind of the higher quality the outputs, especially in the case that when you know that the input point cloud is not having any kind of noise, then obviously like radial basis function might be kind of the best option. But in any case, like if you want to like perform the radial basis function, the approximation, we first need to get the surface number information. And for that, like actually we might need to first run the moving least squares in terms of like the estimating the surface number for each of the point. And just like performing the moving least squares may not be the ideal the option in terms of that, because it's not even like also giving the implicit function, a single implicit function over the entire the shape. It's basically it's locally fitting each of the function for each of the local region. So in terms of that, it's basically not giving some kind of the globally optimal the output. But the good thing of the moving least squares is that it will be way faster. So if the computation time is also very important for some of the applications, like taking the moving least squares might be kind of the better option than the radial basis function. Is this clear? Any questions on this? So if we go one step further, the thing is that, so here the question is that if we can assume that the surface numbers are basically given or basically estimated using the moving least squares or some kind of the ways, can we also compute the signed distance function from the point cloud without basically performing any kind of global optimization and also without basically explicitly fitting some kind of polynomial function into the local region? So this is kind of the another the idea in terms of how we're gonna basically get the signed distance function from the point cloud, but while also assuming that the surface number information is given. Okay. So here basically the idea is that it's kind of like the same thing with the moving least squares. So we are going to say like what's kind of the point that we are making some kind of difference from the moving least squares. But now actually we are going to say that actually we are finding a function in terms of that we are approximating the value at the pi, right? So we know that for all the points that we have in the input point cloud, the signed distance the value that we are basically estimating with some kind of some approximation the function here should be 0, right? So we are finding such kind of the function which will be basically 0 at this point for all the points that we have in the point cloud, while basically approximating this function value with the Taylor expansion. So this is nothing but basically the same the Taylor expansion, right? But given some kind of any kind of query point here. So given any query point which is close to one of the points that we have in the point cloud, this is the form of the Taylor extension, which can be written like this. So now the thing is that now we are going to represent this function with this kind of the function value at the query point and also the first order the gradient, and the second order the gradient, and so on, right? So this is like another way that we are basically parameterizing the function value here in a way that approximating the function value of the at the any of the point that we have in the input point cloud. And we know that this should be 0, right? So here the question is that how we can basically find the function which is like now parameterized in this way with the zeroth order and the first order and the second order like the derivatives in a way that the function value becomes 0 for all the points that we have. So basically nothing but just using the expansion for the approximation. But basically, this kind of the first order kind of the approximation and it can be only used when the query point is close to these kind of the points, right? So we are basically also solve this kind of problem as the the least square descent, but also still using the weight function. So we want to basically minimize this function while just taking the weight here. So we are basically having some kind of the higher weight when those kind of the point PI is close to the query point, and having the lower weight when the PI is basically the farther from the query point, right? Then this becomes that now we are representing the function here f as kind of the zero order, the first order kind of those kind of the terms, while basically finding those kind of parameters by solving the least squares, right? Now you can see that if we take the first order the approximation, this function can be written in this way. So S0 is the function value at the query point here, and S1 becomes the first derivative of the function. Make sense? And actually, you can see that this is exactly the same form of the moving least squares, right? Did you see some kind of the analogy between this and the moving least square, the formulation? So in the previous slide, what we have seen for the moving least squares is that it does basically having this form, right? For the first order, the approximation, right? But while we have some kind of the explanation for the same formulation, actually you can say that these two are exactly the same thing. The only thing is that now we are reparameterizing the vector A into the normal vector, the S1 here, and also having S0 instead of the A0 here, right? So this is actually slightly different kind of explanation for the moving least square formulation, especially for the first order case. But while reparameterizing the A into the S1 which is basically the normal vector here. Actually, the not normal vector is actually the gradient of the function at the query point. And then we are having the S0, which is having this relationship with the A0 here, right? The same formulation with the moving least squares. So the thing is that now we want to solve this optimization with respect to both the S0 and the S1. Make sense? And here the thing is that we are going to use some kind of some crude approximation in terms of that instead of like basically estimating best the gradient of the function at the query point x here. So S1 is basically the gradient of the function at the query point x here, right? And we are going to use some kind of the very crude approximation in terms of that now replacing the gradient of the function at the query point as the gradient of the function, not at the query point, but each of the point pi here. So this is really bad approximation, but let's see what happens when you use this kind of like the bad approximation. So if we replace the S1, which is the gradient of the function at this query point, with the gradient of the function at this, like each of the pi here, what is this? The gradient of the sine distance function for each of the points is actually the surface normal direction, right? So what we want to do is that we are not using the S1 here for all the points, but we are going to change this S1 by taking this kind of really bad approximation in terms of replacing this gradient as the gradient of the function at the point pi here, which becomes basically taking the surface normal information, right? So based on this kind of some approximation, basically what we can see is that now we are replacing this S1 here into the normal vector here. Then now this optimization becomes nothing but just getting the value of the S0. So we are basically replacing the three variables here as kind of the surface normal information for each of the point. But based on this kind of the very bad approximation, what we can say is that this becomes like very simple the optimization because now we are just getting like a scalar value, right? Only one single value. So if we solve this problem, then actually this S0 was basically the function value that we wanted to get for the query point. And you can see that actually this function value can be given into this simple form. Make sense? Any question on this? So this is not directly related to the radial basis function, but if we basically try to interpret this kind of the output, the formulation in the perspective from the radial basis function, this is the case that we are having the weights, which is not constant for all the points, but depending on which query point that we have, we are basically having some kind of different weights here for each of the point here, and then basically having some kind of the weighted sum of the corner function here. And also from the perspective of the moving least squares, what we can see is that this is not basically fitting the plane at the query point, but we are using the pre-fitted the tangent planes for all the points in the input point cloud, and leveraging that information to calculate the implicit function for the query point here. So this is basically not exactly the same with like what we are doing in the moving least squares, but we are basically using the pre-fitted the planes. We are assuming that the planes are fitted for each of the point in the input point. And we are basically using this information to basically get the implicit function for any query point. And the good thing is that with this kind of the approximation, we can directly calculate the function value with this kind of the simplest form. Make sense? So if you see the assignment 4, the assignment 4 will be basically about implementing this implicit the moving least squares and see what sort of the output shape that you're gonna get. So what we are going to do is that we are going to provide the point cloud actually in the 2D space, not in the 3D space. Points, and also we are going to provide the normal information as well. So based on the points and the normal information, what you need to do is that you need to basically compute the sign distance function into these like implicit moving least squares. And then in the next lecture, we are also going to discuss how we're going to convert the voxels into the mesh. So which means that given this kind of the point cloud with the surface normal, now you can calculate the sign distance function either with the implicit moving least squares or like radial the basis function, and evaluate this the implicit function for each of the voxel. It's not the voxel in the cell in the 2D grid, and then you can apply this kind of the idea in terms of like converting the grid into the mesh in terms of getting the final kind of the mesh. So in the 2D case, it will not be a mesh but some kind of the contour in the 2D space. So implementing that will be the last assignment in this course. And while the assignment 4 will be about implementing the implicit moving least squares, what I recommend is to implement all the things, not only the IMLS, but also the radial, the basis function, and also the moving least squares as well, and see some kind of a difference. So that will be also kind of the last assignment. And also the thing is that while we discussed the idea about some kind of doing some global optimization, the radial basis function was doing some kind of the global the optimization in terms of like getting some kind of the weights for each of the point, right? But this is still the optimization to determine the weights for each of the point. It's not giving some kind of the optimal some sign distance function over the voxels, right? So this is while this kind of doing some kind of the global optimization, still it's not the kind of the best way to get some kind of the implicit function over the voxels. So what we are going to discuss next time is basically the kind of the even better the approach in terms of like doing some kind of the real the global the optimization, not for the input points, but also for the points over the 3D grid, in terms of getting some kind of the some sign distance value or some kind of occupancy value for the given some kind of the oriented the point cloud. And then we're gonna also move on to this topic, like how we're gonna basically do some kind of conversion from the pixels into the mesh. Then based on these kind of two building blocks, we will be able to see how we can do conversion from the one representation to the other representation for the all the kind of the ways from the one to the other. So this is kind of like what we are also going to discuss next time. Okay, so any questions on this? So I recommend you to basically check out some more details in some formulations there and see how you can implement this in your assignment. So I'm going to stop here, and then we're gonna continue the discussion about like some kind of way to doing some global optimization from the conversion to the point cloud into the implicit function. And then based on that, we're gonna also see how we can do the conversion from the voxels into the mesh. And I will see you next Monday. Thank you.